Wow, I think you're going to like this. We're really getting into the use of vectors here. Do you remember the question I asked you at the end of the last presentation? It was about this sort of statement here. Here we are. What can you do with a vector which is perpendicular to two others? What can you do with, aka also known as A cross B? What can you do with that? And I don't know whether you thought about areas and volumes, because in calculating many areas and volumes you need a perpendicular vector, don't you? And also, I don't know whether you might like to look at these and think of another result we had. The size of A cross B was equal to the length of A by the length of B by the sine of the angle between them. So not only are you creating in the vector product a vector perpendicular to two others, could be very useful, but also it has this length, and I just think you might remember that that's used for other stuff as well. Okay, so let's go down and have a look at these interesting shapes and the sorts of things that we can do in 3D land with vectors, because it's going to get very interesting now. So come down and let's have a look. And the screen clippings here are from Hayes and Harris publications, so you better get their book, would be a good idea. Areas and volumes. Let's have a look first of all at a triangle. I guess that already occurred to you, that little formula back there for the size of the cross product had something to do with a triangle, because a triangle, here you are, if it was defined by these two vectors with an angle between them, what can you say? Well, I think its area is a half AB sine theta, isn't it? So it's a half the vector product. Did you spot that? Come down, let's prove it. Here we are. So the area is half the product of two sides sine of the included angle. That is the non-right angled triangle formula for area. So it's half the product of A times B sine theta, and we've said that the size of A cross B is exactly that. So, wow, that was an interesting one. So if you define a triangle with two vectors, half the cross product gives you the area. Nice. Okay, could use that pretty well, I think. Let's go down and do some more. And you might like to write that result down in a little note form there somewhere. So here we are. What if we have a triangle ABC and we're given just the vertices in 3D? A good way of finding the area of that triangle is to say, well, let's first of all see what we're doing. ABC labelled around the figure. So let's use AB cross AC. Okay, because that will give us length of AB, length of AC by the angle cosine of the sine of the angle between them. Okay, but you could use any pair. You could use AB and BC. Okay, so the idea here is to just have a little diagram and go from a point outwards to the other two and define the triangle in that way. So it's half the cross product. So we need to find AB. Just remember, AB is 2 take neg 1, which is 3. 1 take 2, neg 1. 4 take 3 is 1. And here's BC now. Doing AC. 0 take neg 1 is 1. 5 take 2 is 3. Neg 1 take 3 is neg 4. So we're going to do the cross product of those. And just remembering how to do that, I think, again, we would use the determinant of the matrix 3 by 3 here. So you go I, J, K, 3, neg 1, 1, 1, 3, neg 4, to get these little 2 by 2 matrices in here. That one, and then this one, 3, 1, 1, neg 4. If you do that, you would have the opposite sign in here. Remember, negative for that one. If you do it that way, or interchange them, get this. So remember, this is very important, this cross product method. Very, very important. And then the last one. So it's the determinant. It's the size of all of that. And this is going to give you the vector. So this will give you our vector. And then we need to take the size of that vector. Okay, so you want the matrix in there to give us that, and then the size of it. Okay, so here it's a half, each component squared and added for the length, half of 2 root 270 square units. So they've drawn their diagram over here, and so you need a little sketch to see which way you're going. So just remember how to get that cross product. It's very important. All right, let's do another one. Let's see if we can develop a bit more. What about a parallelogram? Well, of course, a parallelogram consists of 2 of these triangles, 1, 2. So you're going to double the area of a triangle, and so you're going to have just the straight size of the cross product, AB sine theta this time. Let's have a look. I thought they had a proof here for this one, so we can do a proof for that one. The triangle was a half that, okay, and we have a parallelogram is equal to 2 times the triangle, which is therefore that idea. All right, we'll have a look at a parallelepiped. Now, a parallelepiped is this sort of shape. It's a parallelogram in cross-section and uniform cross-section as you go this way. So you can see the end face is a parallelogram and it's uniform going back there. So there's an interesting result. Where did that come from? That the size of a vector dot the cross product of the other 2. So here we are. We do the cross product. I'll just get rid of this. We'll do the cross product of these vectors that define that base there, and then so they're thinking about it as a uniform cross section of that, and it's uniform going up, and it goes up along the track of vector A, if you like. So here it's the size of, here this modulus, or the size of the determinant of this. Now, how did that come about? Well, let's have a look at the proof for that one, because this is a volume now, okay? Its volume is this. Okay, so let's have a look at that and say, well, the volume of a parallelogram is the area of the base times the perpendicular height. Okay, so that's the uniform cross-section sort of idea here. Okay, so what is the area of the base? The area of the base is a parallelogram. It's a parallelepiped. So it's the size of B cross C. There we are, if that's vector, and that vector defines the base, and we want the perpendicular height now. Okay, so that's AN. Okay, now what is AN? Here it is. The sine of theta is AN over A. Let's just get rid of this. So I'd like to draw this triangle down here. Theta, and that's A, and you want AN. So AN is AN over A, up here is the sine of theta, opposite over adjacent in that right angle triangle, because it's the perpendicular height we're doing here. Perpendicular height. Okay, so you can say that it's the size of the cross product times the size of A sine theta. Okay, so let's put A out the front by B cross C by sine theta. Okay, well, we don't recognise that too much. Let's look at theta though, and there's a trick here because we want to get it into cos theta. You'll see why in a minute. So here theta, let's do this here. Theta is there, that's A, and this is AN. Okay, so here B cross C is the vector going up here, isn't it? B cross C, perpendiculars of the base, which is B and C in the base here. So B cross C is going up there. So what can you say? What's the angle between A and B cross C? Well, it's this one in here, isn't it? Phi. Okay, so what have we got here? What's this really saying? Well, the length of A by the length of B cross C, sine of phi is the same as, sine of theta is the same as the cos of phi. Look at it here. That is the angle between the vectors, same as that one there. Now, if you have these two are complementary here. These two add up to 90 in a triangle, and remember the sine of those, the sine of theta equals the cos of 90 minus theta, and that's phi here, because phi, the angle between the two vectors, is that one in there, which is the other angle in their triangle. So now, why have we done that? Why have we changed the theta to phi? Well, let's just scrub this a little bit out here, because now what have we got? We've got the length of a vector by the length of another vector, the cross product, by the cos of the angle. And that's called the dot product, isn't it? All right, just remember, A dot B is length of A by length of B by cos of the angle between them, which here is, hang on, we'll just leave that as theta because that's the definition. So here we've got A dot B cross C, so that's a single vector, is length of A, length of the cross product, by cos of the angle between them. So that we have actually got that. We've come into it from that particular angle there. Okay, so it is, the volume is the determinant, or the size there, of the scalar product A dot B cross C. Okay, now, that's and here we've got to state cos of phi is going to be positive here. So here, what are we going to do with this? Well, that's pretty powerful. If you can define a parallelepiped with these three vectors, A, B, and C, you can find its volume using vector methods. That's a pretty powerful tool. It would be hard to do that in coordinate geometry to find the volume of that shape. Okay, let's come down and have a look at the next one, a tetrahedron. Now, that's an interesting one. That, of course, is a portion of a parallelepiped, and we're going to look at that in a minute. It's actually a sixth of the volume of a parallelepiped. So it's a sixth of the, here we are, the determinant. So this first bracket here is the determinant of that matrix. Okay, you could actually say the determinant of that matrix, and then this is the, so that's a determinant, and this is then making it positive. That's the size of that value, okay, because we want a volume which is positive. So we're using the idea of basically it's a sixth of a parallelogram, and here it is here, of course, of a parallelepiped, sorry. So the volume of this is a third the area of the base times perpendicular height, and if we go through there, of course, we've got the same sort of expression here. The area of the base is a half of the parallelogram here, and that's going to give you a sixth. So that's the only difference there. We've got a half of the base there, and then it's a third for a tetrahedron, third the area of the base times perpendicular height. So it's actually a sixth of A dot B cross C. So I'm not sure whether you're aware of this. The volume of the tetrahedron, a third the area of the base, and then times the perpendicular height. So it's coming out to be a sixth of the equivalent parallelepiped. Okay, so the rest of this is exactly the same thing. It's really relating this shape to the whole parallelepiped and looking at the effect of the base and the height there. Okay, well, that's going to be useful, because how would you do that in coordinate geometry? That would be a fair challenge. So let's come down and actually see it in action. Find the volume of a tetrahedron with vertices that one, that one, that one, that one. So you need to draw a diagram, I think. And you can start anywhere. P, we usually go around the figure, but here PQRS. You need to define it with three vectors, PQ, PR, PS, or you could come the other way, RQR, PRS, or from any vertex, because you can't really spot this in 3D as to which one's where. So here, to define that tetrahedron, you need to have three vectors. These will do, P to Q, 2 take 0, 3 take 0, 0 take 1, need 1. So we have those three vectors. And you could use any three between those 4 points there. Okay, so the volume now is a sixth of the size of the determinant of that matrix. Okay, now, do you agree that we saw this before, the scalar triple product, A dot B cross C, so that's a vector, that's going to be given by 2 by the determinant of this, the cofactors in here. So here we've got, this is our little matrix down here, which is going to give us our 2 by 2s. So there's 2, 0, neg 2, 3, same as before. And if you take it just as it is there, neg 1, 0, 1, 3, that would have to be a negative if we do it that way. Remember that. Okay, so you need to get the determinant of that 3 by 3, which is given by this thing here. Okay, so you've got your little cofactors, 2 by 2s down there, and the overall determinant is, of course, this by that cofactor, then this by that, and then neg 1 by that. So overall now, it's the size of that A dot B cross C. Okay, so here we are. If you multiply it out, 2 by 2 is 6, take 0, and then 0 by 1 is 0, take neg 3 is plus 3, then 2 take 2 is 0. To get those components there from the 2 by 2 cofactor matrices. Okay, and so the overall answer to the dot product is this one here, which is 21, and you want the size of that, so that's just the same thing. 21 on 6 is 3.5 cubic units. All right, so it's all coming together. Just remember the way in which you will do that using determinants of a 3 by 3. Similar to what we were doing with IJK. Can you see that we've replaced the top line here when we were doing B cross C before? We've replaced that top line, which was IJK, with A1, A2, A3 to produce the dot product there. Because the determinant is each of those determinants times by ij and k in the simple cross product, and then change it to 2, 3, neg 1 in this application. Okay, get rid of that. All right, so let's come down here now and have a look at doing some exercises. So area of the triangle, we've seen one of those. Parallelograms is just going through trying to get the overall rules, if you like, or formulas into action here. This one's interesting, total surface area of the tetrahedron. You might like to look at what are the surfaces of a tetrahedron, triangles I think, and think about what you'd do with those. All right, so pause it and have a go at those. Okay, let's have a look at the rest of them now. Okay, 6, 7 and 8. Okay, so watch the ones down the end here, because they are sort of extension problems, and well, maybe 6 as well. So have a go and think about that. Okay, going to bring up the solutions now. So what's this? So question 1, A, B and C. We need a bit more down the bottom. C and question 2. And let's go to question 3. And question 4. I'm looking at the 4 faces there of the tetrahedron. Face 3. Just looking at all the areas there. Face 4. We'll start to look at question 5. Okay, the rest of question 5. Let's look at 6. 6 and 7 there. And just come down. And 7 and 8. All right, so have a look. Are you getting the idea? Pretty powerful stuff. We didn't really realise when we were finding the cross product, the vector perpendicular to two other vectors, that would be quite this useful, I think. All right, let's go on and see what else we can do. And there's one little thing here. This is interesting. A test for coplanar points. I suppose the equivalent of what, collinear points? Oh no, we could do collinear points in 3D land as well. So coplanar points, are they all in the same plane? Coplanar points. Now, they either are coplanar or form the vertices of a tetrahedron. Do you get that? So let's take A, B, C, and D. Now, if you join them all up, let's join them up here, with vectors, then the sum of vectors around that closed figure should be 0. But if they lie all in one flat plane, like that, it's just a flat four-sided quadrilateral. Now, if they don't, let's say the plane is defined by A, B, and C. Let's say D is above the plane a bit, up here, somewhere. Let's just draw it. I'm going to have to draw a tetrahedron. So let's say D is off the plane. So all of a sudden, that's like that. And you've got a tetrahedron. It's either one thing or the other. As soon as one point is not on the plane defined by the others, do you recognise that this plane has to be defined by two vectors? Let's say AB and AC, or you could do it AD and have a plane going up there, AD and BD. But two vectors is enough to define the flat surface. One vector is not. 2 points lie in an infinite number of planes. 3 points define a plane, don't they? Define a flat surface there. And all you've got to do is show that you haven't got a tetrahedron, if you like. Okay, so what would that mean? If you don't have a tetrahedron, it's not like this. The volume of the tetrahedron would be 0. So what we're going to do is take 4 points, and see if we can work out the volume of the tetrahedron that it forms. If that volume is 0, the points don't form a tetrahedron and are therefore coplanar. Simple idea, interesting, isn't it? So let's come down here. If a tetrahedron is defining vectors, then the volume is that, and what we're going to do is therefore find a 6 of the scalar triple product here. So this is a score called a scalar triple product, because it's a scalar, because it's a dot, and it's a triple product because you've actually got it dotted with a vector product in there. Okay, so let's have a look now. So it's a triple product because you've got 3 vectors involved. All right, so down here, let's have a look at the book way of doing it. And just go back up here a bit. I'm not a real supporter of this because if you're asked to show that points are coplanar, I think you really have to establish this, whereas the book just uses it, okay, as a routine thing. I think you have to establish that that's the way it is. So if you have A, B, so what they're saying here, if that's position vectors there, then AB, AB is B take A. So you go into using position vectors for AB, BC and CD. And therefore you're wanting to say that the scalar triple product is 0. Therefore no tetrahedron exists. I think you need to establish that. Okay, so I'll show you an alternative, but here it is. You're getting AB, AC and AD, and then your dot doing the scalar triple product, which is that, comes to naught. Therefore ABC and D are coplanar. I prefer to see it done directly. So here, just do AB. So you're considering A, B, C and D somewhere. Okay, so what are you going to do? You can do A, B and do it just between them. 3 take 1 is 2, 2 take 2 is naught, and naught, so it's that vector there. Same idea, but leaving out the position vectors. So then you could do A, we've done that one, AC, and you could do any pairs here. AC is 2 take 1, etc. So it's 3, 5. And maths is the same, it's a way of thinking, that's all. AD. So you've got to define the tetrahedron with 3 vectors there. We don't know where D is, let's say. So D, AD, 4, neg 5, 3. And you could use anyone. You could start at DB, DC, DA. Any 3 defining vectors. Just thinking in your mind here about what's happening. So start at any point, and the 3 defining vectors are those coming from that point 3 out to the other 3 vertices, or possible vertices. So now, the volume of the tetrahedron is equal to a 6 AB, the size of AB dot AC cross AD. Okay. AB cross AD, and the size of that. Okay, and so then you work out AB dot AC cross AD. It's the same maths as over here, and when you work that out, you're going to use this determinant here, and you get 0, therefore no tetrahedron exists there, therefore coplanar, because the volume is 0. I think you should mention that you're looking at the volume of the tetrahedron there, and that it comes to 0, therefore no tetrahedron exists, therefore coplanar. I think particularly in a show that question, it's important not to go by basic rules here. I think you've got to show that you understand what those rules are, and I'd go cut to quite straight to the chase and not use position vectors, but use the actual vectors between the point and go through the step, volume, etc., explaining what you're doing, and then looking just at the part that's going to define it, which is that when it comes 0. You say, well, therefore there's no tetrahedron. All right, have a look at that. Okay, so come down, and here is the last 2 questions for you. So have a go. The solutions will be in position vector form. I think I prefer you to do the way that I just gave you there, and that's to look at the tetrahedron like this. Not a very good tetrahedron there. Start at any point, and the defining vectors are going out to the 3 other points, and then do the scalar triple product between any pairs of those vectors. It doesn't matter which way. You could be looking at the tetrahedron from underneath or from this side, so it doesn't matter which ones you choose there. You start with a defining point, let's say it's D, and go to A, B and C, okay, or P, Q, R, S, whatever. Start at a point and create vectors out to the other ones, and then try to find its volume. All right, I'll leave you with that. Have a go, and I'll show you the answers now. There's 9 A and B. Check the working because it's a show that. Show that's are dangerous. Show. You've got to show. Okay, you know the answers. There's nothing for anything. There's no mark for that because you asked to show it. It's really, have you conclusively shown it? All right, let's have a look at 10. And there we have it. All right, so it's really exploded, hasn't it, in this 3D work with vectors. Exciting stuff. So I hope you're enjoying yourself. Go back over it and check it out. I'll catch you in the next presentation. Cheers for now.